Well, I think I probably have to.
It's a pleasure to have you here. And we are recording your talk. And thank you for coming.
Yeah, thanks a lot for inviting me. And yeah, I'm Marina, and I work at the Vrije Universiteit from Amsterdam. And also I'm affiliated with Tinbergen Institute. This is a collaboration between different Dutch universities. And yeah, if you're part of one of those universities, you can also be affiliated to the Tinbergen Institute. And yeah, today I'm presenting a paper that is joint work with my colleague who works at the same department. He's actually my office mate, Yi-Song Lin. And yeah, the title is purely theoretical, but we also have some climate-related applications. So the title is Sieve Bootstrap Inference for Time-Varying Coefficient Models. And yeah, this is the outline of the talk. I'll start with the empirical application to see, so you can see what our model can do. And also I think it fits the project to start with the application. And then I'll switch more to the econometric side to give another motivation, not only from the application side, but also from the econometric side. And then I'll present the model and our estimation strategy. And then the main part of the paper is the Sieve bootstrap and how to construct confidence bands. And then briefly, I promised my co-author to also show the asymptotic theory. That's not my part. And then maybe some simulation results depending on how it goes with time. And yeah, feel free to interrupt me if you have questions. And yeah, so our application is to the European emission trading system, the EU ETS. And it's a cap and trade system. So all the firms that are covered by this sector, they have to surrender allowances or permits for every ton of CO2 they emit. And they get these allowances, either there's a market where they are traded, but actually some of the companies actually get them for free. And then they can match their emissions with allowances and trade whatever they have left on the market or buy extra if they need extra allowances. So that's the cap and trade system. And the EU ETS is one of the largest and also oldest cap and trade systems. And it covers 31 countries, the EU, and some extra countries. And it covers around 40% of the greenhouse gas emissions of the EU. And most of the emissions or most of the companies that are covered by this system, they come from the power sector or energy intensive industries, like for example, the cement production. And then also at some point later, also civil aviation was added. And this market started operating in 2005. And it's divided into different trading phases. And yeah, the first phase was more of a trial phase. And then, now we are currently in phase 4, which started in 2021. So it's this new phase is very recent. And then between those phases, they often change the rules quite a bit. For example, all the allowances that are not valid anymore. So that's why we actually don't analyze phase 1, but we start analyzing phase 2 up to very recent data, because all the allowances that were issued in phase 1, they lost value. So the price of those dropped to 0 at the end of phase 1. And yeah, they have also a lot going on in the market because the market was not really functioning super well at the beginning. So they tried to make a reform to actually reduce the surplus of allowances that was in the market. And the current goal to the end of this current phase, which is until 2030, is to achieve a 43% emission reduction compared to the start of the phase, or the start of the system in 2012. And the cap, so the amount of emission of permits that is given to the market, always decreases linearly year by year. And now recently they also increased this reduction factor from 1.74 to 2.2% per year. And so this is the allowance price. And so this is the time series of allowance prices that we analyze, and this is the these are very new results. We updated our data series. In the old version of the paper, it ended in 2018. And 20 years of 19, 20, and 21. So yeah, the development we also wanted to incorporate, because if you cut in 2018, there's a lot that interesting things that happened after 2018. So we also updated our data. Yeah, and there, in this market at first, when this huge increase started, at first because this starts a bit earlier, right, than when all the other markets start experiencing this upward trend, and there was a big reform, and then they started to experience upward trend after this reform. So they're finally working because they, the prices are increasing. And then in the, there's an empirical literature in this market as well. So in theory, they have some clear, the price, and maybe I can also mute.
Yes. Maybe you can speak. Maybe Usman, could you mute it?
I wrote to him, but I couldn't read.
Maybe just.
Usman,
maybe I can.
Maybe you can mute.
I don't know.
Yes, I cannot. I don't know why. I cannot. I can just.
But if I mute my laptop, people can still hear me, right? But I cannot hear the sound.
I don't know why.
No.
But maybe now people should still hear me, but I mute my computer.
Okay.
Which means we cannot hear questions, but if people raise their hand, we can see questions.
Okay.
At least that's what I think is happening, right? Because I just don't hear anything anymore from my computer. Okay. So in the theory, there are very clear price drivers. If you use the theory of environmental economics, and the coal and the gas price should be the most important drivers, because, as I said, the main companies that are covered by this market are from the power sector. And in the power sector, you have this fuel switching relationship that you can either use coal or gas for electricity production, depending on the relative price between them. And the coal price should have a negative effect in theory on the allowance price, because coal is more dirty and it produces a lot more CO2 in the electricity production than if you use gas. So then if the price of coal rises, then the producers would switch to gas, which is cleaner, and that will reduce the demand for allowances. That's why the reason there is supposed to be a negative effect, according to economic theory. And for the gas price, it's the other way around. Gas is a lot cleaner, so when the gas price rises, they will switch to coal instead for electricity production. And then, this is cleaner, so they switch to coal, which is more dirty, so there will be a higher demand for allowances, so the price should rise in theory. So that's the relation why one has a negative and one has a positive effect in theory. And then, also economic activity should play a role, of course, because the more they will produce, the more emissions we have. That's quite a clear relation. And then also weather variables, depending on how much air conditioning, for example, or heating is used, and also how much renewable electricity is produced. But then when I started looking at the empirical papers, I saw that it's really hard to, for example, if you run a regression analysis, to establish those in coefficients, this relationship. And so there are some previous studies often find an insignificant coefficient, or also a wrong sign of the coefficient. So for example, a positive sign for the coal coefficient instead of negative. And then they start, for example, splitting the sample and running one regression for the first phase, one regression for the second phase, and so on. Or they take out outliers, or they do an analysis.
Reduce approach in the literature was on the linear.
Mostly, there is one paper that allows for regime switching model,
which is
non-linear, and they actually say they give evidence for non-linearity in the market. And yeah, and also depends a lot on what kind of data series you use. So what is the source? And then there's also co-integration analysis, because most of the data has a unit root, but also there is no evidence for a long run stable relationship. So we thought also maybe going into the direction of a nonlinear relationship to see that maybe the relationship is just unstable. That's what people already do by splitting into different time periods. That could be one explanation. So we thought with our model and approach, we can add to the literature by just running a very flexible time varying regression to see what the data tells us without splitting any data sets, and just putting the data in and see what the data tells us. And indeed, we find some evidence of time variation in the coefficients, but in general, also it's really hard to establish this relationship even with this flexible approach. And so this is the main drivers of interest. I plot them together with the allowance price. So here we have in blue the allowance price, and then on the left side we have the coal price with it, and on the right side we have the gas price with it. And you see that for coal and the allowance price there is some opposite movement visible in the series. And for the allowance price and the gas price, there are also quite some similarities. But of course, at the end, all the prices, as you mentioned before, they rise, but it comes quite a bit later compared to
the in inverse correlation, no? Type of negative relation.
In this case, that's what we would like to see, but it's quite hard to establish. So then we just ran also a linear regression to see what comes out when we use our very new data, because now the data goes to the end of 2021. So we have from 2008 to 2021 data available on the allowance price, on coal prices, gas prices, and also oil prices, and the stock index, and also temperature data. And most of the series contain a unit root.
Yes.
So,
because, sorry, I interrupt but because it's clear that these series are all non-stationary, and do you think to some transformation of the series or not?
We take the first the log return, actually the log returns, but we also test the logs. The logs are also non-stationary, so we take log returns because we need stationary regressors. But then we also develop a test for parameter constancy, and we apply it to those models, and that's also Bootstrap based, and we also have this in the paper, and it rejects for both versions. So one includes the oil price as an indicator of economic activity, and the other one is the stock price as indicator of economic activity. And in both cases, the parameter constancy, according to our test, is rejected. So there is some evidence to apply a more complicated, non-linear model. Actually, our model is linear, but the coefficients are smooth functions of time. And I'll show the model later. This is just to see the some first results what the model can do. So this is then when we apply the non-parametric or the time varying coefficient model. Then the black line is the coefficient estimate, or also the time varying intercept, which becomes a trend. And then indeed we see for the coal coefficient it is negative, but then also turns positive at some point. And then we have, the blue ones are pointwise confidence intervals, and the red dashed ones are simultaneous confidence intervals. But there we see, when we look at the simultaneous ones, they are really wide. So there we cannot say too much, but here the gas coefficient indeed is positive and significant for some periods, also using the very general simultaneous confidence bands. So they are simultaneous 95% confidence bands over the whole sample. So our paper actually adds to that literature that there is some evidence of time variation, which explains why when you run a linear regression, you get insignificant coefficient, especially for the coal price, because there is some time variation in that in that variable for sure. So that was just a small contribution to the empirical literature on the EMTS. And now our econometric motivation and our econometric contribution is that bootstrapping is actually already used with these type of models, so the time varying coefficient models. And we checked some literature, especially in energy economics. And we found some papers that are all published, I think, in energy economics that study, for example, price elasticities for energy demand or income inequality and CO2 emissions, or the environmental Kuznets curve. And they all use bootstrapping in the context of these time varying coefficient models. And of course, it makes sense because bootstrapping is really easy to implement. So if you want to construct confidence intervals for the parameter estimates, Bootstrap is easy to implement. It also has good small sample properties, which we show in our simulation study. And if you don't want to use bootstrapping, you have to estimate nuisance parameters, which in this case, we don't have to do because the bootstrap automatically takes care of this. So if you want to go in a standard asymptotic way, you have to estimate the nuisance parameters, which is a bit tricky. And what we found is that the bootstrap validity has not been proven. So the bootstrap is already used quite a lot in this context, but the validity has not been established. And we think it's important to also establish the validity. So our theoretical contribution is that we establish the validity of, in this case, the Sieve bootstrap to construct confidence intervals for those time varying coefficient regression. And we have simultaneous and pointwise results. Those were the two different intervals that you could see on the previous graphs, the blue ones and the dashed ones. And we also develop a bootstrap-based test for parameter constancy, which I cannot include in the presentation because it will get too much. And there is already some literature on simultaneous confidence bands out there that dates back to Peter Bühlmann, who looked at the Sieve bootstrap method, but then the model only contained a non-parametric deterministic trend and no regressors were allowed. And then we talked about this paper earlier by Neumann and Kolse. They have the same model, but then a wild bootstrap approach. And then non-bootstrap papers is this one where they derive simultaneous confidence bands, also not allowing for regressors. No bootstrapping, and then a paper of myself and my PhD advisors, where we look at the autoregressive wild bootstrap for deterministic trend model, but again, no regressors are allowed. The most related paper to ours is this one by Zhu and Wu, and they derived the simultaneous confidence bands based on asymptotic theory for the model with regressors, but they don't use bootstrapping. And we also compare our results to their results. And so this is finally the model. So we have a linear model, but with time varying coefficients. So we have stationary regressors, and then the coefficients are modeled as smooth functions of time. And for the, I also show some assumptions later on the error terms and so on for completeness. But the error terms follow a linear process. So we allow for dependence, but not for heteroscedasticity in the errors. And the estimation is already established in the literature. We use a local linear estimator, which works better than the local constant one that most of the other literature looks at. And there's already a paper out there that originally proposed this, dating back to 2007 by Sieve. And compared to the local constant estimator, the local linear estimator is shown to not suffer from boundaries. And we also look in the theory at the boundary points. And the estimator is based on first order Taylor approximation. So you also get the derivative of the functions, the coefficient functions in there. And then it basically minimizes the sum of squared residuals, but then in a weighted way where we have the kernel functions as weights. And then H parameter is the bandwidth. So this is the local component for the weighting. And then for completeness, that's how the estimator looks like. We are interested in the estimate for the coefficient curves, but we also get as a byproduct an estimate of the first derivative. And you see it has a bit of a form like an OLS, where you have x prime x inverse, x prime y in those components over there. And then here you can see the elements of the matrix. And then bandwidth selection is really important with those kind of estimators, because the bandwidth determines the smoothness of the estimator. And there it's important to also look at data-driven selection methods. And we look at several different ones. Actually, 4 is probably not correct anymore, because we found another one that we combined into a new one that works quite well. So we look at some standard methods that are used in the related literature. One is called Generalized Cross-Validation. We implement this one. Then another one that was proposed in the original estimation paper. That one is based on a Akaike information criterion. And then we adapted two. One is called local cross-validation and one is called modified cross-validation. And we combined it into local modified cross-validation because it works a little bit better, at least in our simulation results. And this one, so normally the normal cross-validation, not modified and not local, works with this leave one out estimator. So you always leave out the observation receiving the highest weight to avoid overfitting. So the modified one is modified to time series data, leaves out several. So it leaves out L to the left and L to the right of the observation receiving the highest weight. So that is the modified cross-validation. And then there's also a paper that makes it local. And we combine these two into this local modified cross-validation, which, as I said, works a little bit better in our simulation study, at least. And now I went back. Excellent. Yeah, and now coming to the Bootstrap algorithm. As I said, this is the main part of our paper. The Bootstrap is a Sieve bootstrap. So it's residual based, which means in the first step, we obtain the residuals from our model. The only non-standard part is that we need to use an over-smoothing bandwidth. So we need a slightly larger bandwidth to account for the asymptotic bias of the estimator. And the rest is quite standard for the Sieve bootstrap. So we fit an autoregressive model to those residuals that we get in the first step, center them, and then draw randomly with replacement from those from the residuals of the AR model that we estimate. And then we calculate the bootstrap errors by putting the dependence structure back in and then adding it to the estimation from the first step with the over-smoothing bandwidth. And then to the bootstrap observations, you apply the bootstrap estimator, this time with the original bandwidth, so the one you got from any of the data-driven criterion. And then, you repeat it many, many times, and then you get the bootstrap quantiles. And those you can directly use to construct pointwise confidence intervals. And then we additionally propose a procedure to construct simultaneous confidence bands. So this is just an overview that you can immediately construct the pointwise confidence intervals from those bootstrap quantiles. But they are only valid for a certain point in time. What we would like to achieve is the simultaneous validity, but we have the simultaneous validity only over a certain set of time points G by our theory, which I will also show later. So it's not, you can in practice take the whole sample, but in theory, we only prove the validity for a finite union of intervals where the width of the interval depends on the bandwidth. And the simultaneous confidence bands, we construct them by this 3-step procedure, which is also originally taken from the paper by Peter Bühlmann. And in the first step, you take all kinds of pointwise errors, with the pointwise error ranging from 1 over the number of bootstrap replications up to the alpha level that you choose. And then for all these pointwise errors, you construct the bootstrap quantiles. And then, you within those point-wise errors, you search for the one that satisfies this criterion, and this criterion means that we want all centered bootstrap curves to that are completely covered by our confidence bands to be as close as possible to, for example, 95%. So if we want to construct 95% confidence intervals, let's, for simplicity, assume for the whole sample. Then we look for this alpha, for which the fraction of bootstrap curves that lie completely within our confidence bands to be as close as possible to 95%. And then this will be our simultaneous alpha level. And
is there a theoretical result behind? Or?
We prove I can show you later in the theorem, but again, it's not I didn't do the theory. That's why.
New papers by with Yahoo.
We have. This is very related. So we compare their method, which is only based on the asymptotic distribution, to our bootstrap method. Okay, so the assumptions. Again, this is not my work. So if you have very detailed questions, I have to forward them to my co-author because he did the theory. But yeah, I think most of the assumptions are standard for invertibility and so on of the linear process. But I think overall we want the Z and X to be jointly alpha mixing, which is I think obtained by assuming X to be alpha mixing, and then you need some extra condition on the density of the error terms. But again, that's just what my co-author told me, I should say. And we have some kind of second order exogeneity condition that we need that is a bit more standard. The rest, those are just assumptions on the coefficient function that they have to be smooth. Then some assumptions on the kernel functions that are also standard in the literature. Then we get a lot of rates for the bandwidth and the over smoothing bandwidth, and also the lag order of the AR model in the bootstrap. And then we have this first theorem that just shows the bootstrap validity. So basically that the asymptotic distribution in the bootstrap world is identical to the asymptotic distribution in the non-bootstrap world. And we also do that explicitly for the boundaries, but I don't show that here because then the slide gets too messy. And then this is the uniform validity, but it's only neighborhood uniform validity. So it only holds within, as I said before, H neighborhoods, or neighborhoods where the width depends on
this sort of band H, no?
The bandwidth, So the width of those depend on the bandwidth. So in theory, we can only prove the validity for a finite union of those intervals, which is more restrictive than what the other paper does, where they don't use bootstrapping.
But there, after the canonical product, you are considering a sort of decomposition of the covariance matrix.
Yeah.
Okay. So the way basically lambda is just the diagonal of the eigenvalue, something like that.
So
okay.
But
just use it.
I mean, there's some dependence within those H neighborhoods, and we show that this is reflected in the bootstrap world. And then we have a simulation study where we look at two regressors, and the coefficient functions are different. One has two peaks and is a lot more volatile, and then one is more simple to estimate. So this is a little bit complicated because usually a bandwidth is selected for the whole model. So here, if we want to estimate it, we would want a smaller bandwidth to also capture the local peaks. And for the other one, it's a bit easier probably to estimate. We choose those two coefficient functions inspired a little bit by our empirical application, where the gas price coefficient had a bit of this two-peak shape, and the coal coefficient should be negative, which actually it becomes positive, but that's how it should behave according to the economic theory. And yeah, this is just the coefficient functions written out. And we have a dynamic specification between the regressors. And yeah, the error follow an AMA process, and we vary the dependence a bit to see how the bootstrap performs with different values for phi and psi. And yeah, we have 2000 Monte Carlo replications. We have a sample size of 200, so it's rather small. And yeah, we use quite standard kernel in the literature, and we look first at fixed bandwidth and then at a huge range of bandwidth from 0.06 to 0.21. And then we also look at the data-driven bandwidth selection methods, but those I don't have yet in the paper. They were still, we still have to compile them into tables because that's really recent for our revision of the paper. And then, yeah, we consider simultaneity over intervals or union of intervals, like according to our theory, but also we consider simultaneity over the whole sample. This is one example where you can see the form of those intervals. So in this case, we have the true coefficient in beta, the estimate in blue, and then the confidence bands in dashed, and they are simultaneous over the union of those four intervals. So for example, you can say something about the beginning and the end of the sample simultaneous. That's just to visualize how those intervals look that we chose. And yeah, those are our results. And yeah, just the main takeaway is that for the beta 1 parameter that is a bit more volatile as expected, when the bandwidth gets too large, the coverage drops. And yeah, the pointwise coverage is really accurate for 95%. And also when we have dependence. And then for the simultaneous coverage for the different intervals that we choose, and also for the full sample, depending on what bandwidth you choose, it's up to 92% for the whole sample, which is not allowed in our theory. And then with this smaller sample size of 200, the asymptotic method really has some problem for the whole, the whole interval. And yeah, this is because the bands that are obtained with this method are really narrow. For this, I also show this is the empirical coverage for beta 2, so for the other coefficient, which is easier to estimate because it doesn't have as much variation. And there you can see that actually this is much more robust and it has accurate coverage even independent of what kind of bandwidth you choose. And then the length, that's what I wanted to show, is that you see for the pointwise, the length is kind of comparable from our bootstrap intervals and the asymptotic intervals. But then when you look at the simultaneous intervals, then they become a lot more narrow compared to our intervals. And that explains probably the large drop in coverage. And then it's similar for the other coefficient. And yeah, that's already the end of the presentation. So the contribution of this paper is that we show the Sieve bootstrap validity for time varying coefficient model. We also have simultaneous confidence bands. And yeah, we performed an extensive simulation study of which I showed a small part. And we have the application to the EU emission trading system. And yeah, for the future, we would like to extend this to a panel setting. This is also already used in the literature, but also with bootstrapping. And we would like to show the validity of the bootstrap also for independent setting. And then, yeah, we were starting a collaboration with our Institute of Environmental Studies, where people approached us that would like to study the effect of sea surface temperature and soil moisture on soil yield data. So this would also be a natural application where we have two drivers, and then, yeah, the soil yield as dependent variable, because there's also some evidence for time variation. But that, yeah, we are just starting. Yeah, and those are just references. So thanks a lot for attending.
I'm sorry, I expect that you will discuss a bit some theoretical issues.
You mean the theory?
Yes.
I mean, yeah, I didn't do the theory, so I just show. I can just show the theory.
For instance, in your simulation, you choose sample size of n equal to 200.
Yeah.
Why you should not to confirm some asymptotic theory with maybe large sample size?
We also checked 500. We have 400 or 500. And we have both. In the paper, we have both results.
And the convergence you already have also to n is equal to 200. You already have convergence of the.
The Bootstrap performs better, much better in small samples.
Okay. Yes.
So there we don't actually need such a large sample size, but yeah. So our method already performs quite well also with smaller samples, which is more realistic in many applications.
Just one last question. So basically, the dependent variable was the trading system of the EU, and the covariance was the coal price and the gas price.
Yeah.
And can you back to the slide whether you have the coefficient with the time coefficient that you explained?
Okay, with my improvised pointer. Let me see. No, it should work. Let's back, let's forward.
You have to do the heart of. Okay. This one. So basically, in one case, you okay. So the interpretation is that the case of the coal in B you have that it is first negative, and then it comes insignificant, close to 0.
Yeah, over there.
Okay, okay. In other cases, the most positive. Yes. Okay. So this is the interpretation, basically.
Yeah, this is really very new data because we extended the data set by some years. But yeah, the main result is still that you see this negative period, but then it becomes insignificant. So probably that's why there's, yeah, this is just in line with the literature that they cannot find a significant negative effect of the coal price, while it's easier to establish a positive effect for the gas price.
Okay, but I don't see the x-axis is the time there, no? Because I don't see.
Oh yeah, that's the time. Yeah,
that's the time, and it's the same for each graph.
Yeah,
so the peak is not in common. Is it to?
No. This is the exact same time, but yeah, I think I accidentally cut the time axis. Okay. Because I included the new results to present today, and these are just from a few days ago.
Okay.
Yeah, I have a question related to the method. In the papers, in some of the papers you mentioned, such as that of Wu, for instance, they also use not the Bootstrap, but a kind of Monte Carlo procedure.
Yeah.
Because they just build the pivotal statistics, and then they simulate the statistics under a particular setup for which the convergence holds. And they find that it is a good alternative to the Bootstrap. So what about the comparison between such Bootstrap, such Monte Carlo procedure?
Yeah, so we have the results that I showed, they actually compare the two results, the two methods. And this, yeah, so the method of this other paper is indeed they have a simulation-based approach because they simulate from their asymptotic distribution, basically with this method. And we implemented. Oh, now I'm going again in the wrong direction.
They don't simulate with the asymptotic. They instead of using the asymptotic distribution, they for pivotal statistics, what they do, they simulate the statistics several times using a particular setup. For instance, for independent data or something like this. and they find that sometimes it gives better results than the Bootstrap.
Yeah, I mean, they don't look at the Bootstrap. We implemented their method. Actually, 3 different people implemented it. So that we are sure we implemented, we also reached out to them to ask them how they obtain the coverage, because we cannot get good simultaneous coverage for their method.
Okay.
But very good point-wise coverage. So I reached out to them and asked them how they obtain the coverage in their simulation study, and yeah, we didn't get a reply because, I mean, and we had 3 independent people implementing the method, and we use exactly the same parameters as they choose, and yeah, those are the results. So for the full sample, which is supposed to be valid in their case, because it is simultaneous over the whole sample, the coverage is really, really low.
Okay.
But this is for a sample size of 200, but also for, I think, 400 or 500, it was higher, but not close to 95%.
Okay, because from my experience, the simulation-based method works more or less depending on the setup that you use for simulating the statistic. And maybe if the setup that you use to simulate the statistics is too far from the DGP, the data generating process, sometimes it doesn't work so well. But in some cases, it produces nice results. I think it depends on how you apply the simulated based method, because there are several ways to simulate the statistics.
Okay, yeah, I can maybe mute, I guess. No? Okay. I couldn't mute, but I think I could try to, yeah, the sound is already full on my laptop. I don't know why it's so loud. Yeah, so as I said, in our simulation results, it doesn't work, but our setup should be valid according to their setup. But we implemented it following exactly the steps that they mentioned in the paper.
Okay. So it's yeah.
Yeah, and of course we only have the results from the setup that we look at, but I mean it should be valid because it's even for this case where they also allow for heteroscedasticity, and we also have one set of results where we also allow for heteroscedasticity, which is theoretically in our method not allowed, but in their method it is allowed. But even there, the Bootstrap produces much higher coverage. But yeah, as I said, we were really careful implementing their method, and I think triple checked with 3 different people multiple times, and we couldn't find a mistake, and we really followed the instructions. But there we also couldn't find any code that they provide, so we programmed it ourselves.
Yeah. Okay, thank you.
Was there questions, maybe? So it's very hot in the room. Maybe we should just close the session and thank you again. So I don't know how you do that in Germany, it's like that, but here it's. Thank
you.
Okay, so thank you, and thank you for coming.
Thanks.